This video is the first part in a two-part video introducing graph by transformation. Graphing by transformations is a very powerful graphing technique. It allows you to transform any parent function. We're going to discuss 6 different transformations. The first ones that we're going to discuss are called rigid transformations. Rigid transformations change the position of a graph, but do not change the shape of the graph. Our first rigid transformation is a horizontal shift. Now, a horizontal shift is exactly what it sounds like. It moves the graph horizontally, either left or to the right. A horizontal shift is recognized by either plus or minus a number inside the function. So you're going to have x plus 6 or x minus 9 inside the function. If it is a minus sign inside the function, you're actually going to be shifting the graph that many units to the right. And if it is a plus sign, you're going to be shifting the function that many units to the left. So it's opposite. If we want to graph y equals, let's move that into function notation. If we want to graph f of x equals x minus 3 quantity squared, we are going to take the parent function, f of x equals x squared, and shift it to the right 3 units. So to get the parent function, you want to look at x and whatever's going on, whatever exponent there is, whatever radical there is, that tells you what the parent function is going to be. So we have an x and an exponent of 2 tells us x squared is the parent function. Then that minus 3 on the inside tells us to move that many units to the right. So we're going to be shifting f of x equals x squared 3 units to the right. Here in the dashed line, I've graphed our parent function, f of x equals x squared. And now I'm going to show you how to shift it to the right. I'll actually put the 5 points from our parent function on here. And now I'm going to take each of those 5 points and simply move it to the right 3. And draw in our graph. Trying to actually hit all the points. Okay, so there in red is the graph of f of x equals x minus 3 squared. The minus 3 on the inside told us to take the parent function of x squared and shift it 3 units to the right. Our next rigid transformation is a vertical shift, and that's exactly what it sounds like. We're going to be shifting a graph either up or down. A vertical shift, we recognize that that's going to occur when we have plus or minus a number outside the function. So with horizontal shift, it was happening inside, but here we need to see that plus or minus a number outside the function. If it's a plus c on the outside, we're going to go up that many units. And if it's a minus number outside the function, we're going to go down that many units. So if we want to graph f of x equals 1 over x plus 1. Our parent function involves the x and anything that's happening to the x. So x is in the denominator. That tells us our parent function is going to be f of x equals 1 over x. And then we have this plus 1 on the outside. Plus 1 on the outside tells us to shift the parent function up 1 unit. I have our parent function here in the black. And we're simply going to shift these points up 1 unit. Drawing our curve. Shift the other side up 1 unit. And drawing the other half of our curve. Same shape, we've simply slid it up 1 unit. Our next two rigid transformations are reflections. First, a horizontal reflection. This is a reflection about the y-axis because it's going to flip side to side. We recognize that a horizontal reflection is going to occur by having multiplication by a negative inside the function. So you're going to need multiplication by a negative inside the absolute value, inside the square root, inside the parentheses, right in front of the x. If we want to graph y equals the square root of negative x, we're going to start with the parent function, f of x equals the square root of x, and then we're going to reflect it about the y-axis. To get the correct points for this reflection, you want to multiply all the x values by -1. Since it's a horizontal reflection, we're multiplying the horizontal components, the x values, by -1 to flip it over. So here we have our parent function. With the reflections, you may even want to list out the points to help you. So this is going to be 0, 0, 1, 1, 4, 2, 9, 3. To reflect it about the y-axis, we're going to multiply all the x values by -1. This gives us the point 0, 0, -1, 1, -4, 2, and -9, 3. And now we plot those points. And draw in our curve. You'll see it's the same shape. It's simply reflected about the y-axis. Everything that was on the right is now on the left. Our last rigid transformation is a vertical reflection. This is a reflection about the y-axis. We recognize that there's going to be a vertical reflection when we have multiplication by a negative outside the function. So for horizontal, it was inside the function, and for vertical, it's outside the function. And you'll start noticing a pattern. If we look back up to the shifts, a horizontal shift was inside, a horizontal reflection inside the function. A vertical shift, we had plus or minus number outside the function. With the vertical reflection, we're going to have multiplication by a negative outside the function. So the negative will be out in front of the absolute value or the square root or the parenthesis or anything like that. In order to graph y equals negative absolute value of x, we're going to start with our parent function, f of x equals the absolute value of x, and we're going to reflect it about the x-axis. To get the correct points, we're going to multiply the y values by -1. It's a vertical reflection, so this time we're multiplying the vertical component, the y value, by -1 to flip it down. Again, it may be helpful to write the points down to make sure that you get the correct points after the reflection. Our absolute value parent function goes through the points -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. To get the points post-reflection, we're going to multiply all the y values by -1. This will give us the points -2, -2, -1, -1, 0, 0, 1, -1, and 2, -2. Let's plot these points. and then draw in our graph. You'll see once again that the shape did not change. We simply reflected it. Yeah, it's upside down now, but we didn't make it taller or skinnier or anything like that. The shape stayed the same. It's just the position changed. Our next two transformations are non-rigid transformations. This means that the shape is actually going to change. The graph is going to get taller or wider or shorter or more narrow. First up is a horizontal expansion or contraction. We recognize that there's going to be a horizontal expansion or contraction when we have multiplication by a number other than 1 inside the function. So there's, again, horizontal is happening inside the function. And we're going to have multiplication by some number inside the function right in front of the x. Now, this number, we're not going to be talking about negative. We're always going to just be looking at the positive number because as we saw in the previous two transformations, multiplication by a negative is a reflection. So we're just looking at a positive number here, not the negative. If the number you're multiplying by inside the function is greater than 1, it's a contraction. So if we want to graph y equals the quantity 2x squared, we're actually going to be contracting the parent function f of x equals x squared by dividing the x values by 2. I know, it's multiplication by 2, so you would think you would multiply the x values of 2. But since it's happening inside the function, you're going to do the opposite. We saw that with the horizontal shift. When it was plus, we went to the left, and when it was minus, we went to the right. So here again, we're doing the opposite of what the operation indicates. So I have graphed our parent function, x squared. Like with the reflections, I think it is very helpful to write out the ordered pairs, since now we're going to need to divide all the x values by 2. So this is going through the points -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. To get the contraction, we're now going to divide all the x values by 2. This gives us the points -2, 2, -1, 1/2. I divided the y values, didn't I? All right, try that again. Dividing all the x values by 2, we're going to get -1, 4, -1/2, 1, 0, 0, 1/2, 1, and 1, 4. We'll plot these 5 points. And draw in our graph. The shape of our parabola has definitely changed. It has become much more narrow. It has been contracted horizontally. Now, if the c value, which is the number that's multiplying inside the function right in front of the x, is a number between 0 and 1, it's actually an expansion. So if we have like a positive 1/3 in there. To graph y equals the absolute value of 1/3 x, we're going to start with the parent function, f of x equals the absolute value of x. And we're going to do the same thing that we did with the contraction. We are going to divide all the x values by that c. But the reason it turns into an expansion is we're dividing by 1/3. When dividing by a fraction, you multiply by the reciprocal. So really, we're going to end up multiplying by 3. That causes the expansion. I'm going to write out my 5 points and then multiply all the x values by 3. Our absolute value parent function passes through the points negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. And now I'm going to divide the x values by 1/3, but really we're multiplying the x values by positive 3. We get negative 6, 2, negative 3, 1, 0, 0, 3, 1, and 6, 2. Drawing our graph through our points, we see again that the shape has definitely changed. We have expanded our absolute value function horizontally. It has gotten wider. Our last transformation is either a vertical expansion or contraction. We recognize that a vertical expansion or contraction is going to occur when we have multiplication by a number other than 1 outside the function. So it's vertical, so this transformation, we recognize it's going to be outside the function, and we're going to have multiplication by a number out in front of the absolute value, in front of the radical, in front of the parentheses. Just like with the horizontal expansion or contraction, we're not taking the negative into consideration because the negative is a reflection. We're just looking at whatever the positive number is. This time, if your C value is positive, it is indeed going to be an expansion. And if our C value is a number in between 0 and 1, it's going to be a contraction. When the transformation is occurring outside the function, it behaves as we would expect. So when your C value is greater than 1, the graph is going to get taller, and when the C value is between 0 and 1, the graph is going to get shorter. The reason it does what we expect it to do is because we will be multiplying y values by whatever that number is out in front. So in order to graph y equals 2 times the cube root of x, we're going to start with our parent cube root function, and then we're going to expand it by 2 by multiplying all the y values by 2. So we'll start with our 5 points. I'm going to list them out and then multiply the y values by 2 to get the correct points for our expansion. So our points are -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. To get the expansion, we're going to multiply all the y values by 2. So that gives us the new points: -8, -4, -1, -2, 0, 0, 1, 2, and 8, 4. We'll plot these 5 points. And then draw in the graph. The shape has definitely changed. It has expanded vertically. And what we have there in red is the graph of y equals 2 times the cube root of x. See, my words are a little out of order here. This guy should be down here. So here we'll look at a contraction. We recognize that we're going to have a vertical contraction when we have multiplication by a number between 0 and 1 out in front. So to graph y equals 1/2 x to the third, I'm going to start with the parent function, x to the third. And then that multiplication by a half tells me that I want to multiply all my y values by a half, which is going to result in a contraction. I'm going to list out my 5 points. -2, -8, -1, -1, 0, 0, 1, 1, 2, 8, and we'll multiply all the y values by a half to get the points post-contraction. It's going to be -2, -4, -1, -1/2, 0, 0, 1, 1/2, and 2, 4. We plot our points and draw in our graph. We have vertically contracted our parent function of f of x equals x to the third.